Thank you for coming to my seminar. It's really great pleasure to present my research here with the great audience of KIAX and particular Department of Chemistry. I work at the City University of New York, and it is known as CUNY. CUNY consists of 25 colleges, and Queens College is one of 11 senior colleges where I work, and it has excellent track record of education and also research. I am also affiliated with Graduate Center, which is located in Manhattan, right across the Empire State Building. And I'm also actively involved with the PhD education of CUNY. So I am on sabbatical this semester, and I have been working here at KIAX this semester, and it has been really great experience for me. And the motivation and also the experience I gained here will certainly play important role for my future. And I really thank Professor Youngmin Lee and KIAX program for the hospitality and also great support. Before I present my talk, let me also thank my current and former postdocs and PhD students, and also many of the great collaborators that I have worked with and also work with at present. Most of the research that I am going to present today was supported by the U.S. National Science Foundation and also the Department of Energy. And also I would like to thank Dreyfus Foundation for some support earlier, and KIAX and KIAX, in particular KIAX, for support for my visit to Korea. And for the computational support, I also would like to thank the Center for Computational Infrastructure for Sciences at Queens College and CUNY High Performance Computing Center, and also Center for Functional Nanomaterials at Brookhaven National Lab. I want to begin my talk by first asking you a simple question. So what do you think these images are? Anyone? Okay, let me give you one more clue. So let me give you one more image, and also let's also activate this movie. What do you think these are? Any volunteer? Okay, so let me provide you with the answer. So these are actual image of purple bacteria in fresh water. And this is a microscopic image of purple bacteria taken by Scholes and Fleming some time ago. And this is a movie of light-harvesting 2 complex within the purple bacteria. And this is not real. This is actually the movie that we created out of about 40 nanosecond simulation. So it is true that the life on Earth began and also is sustained by photosynthetic organisms. And purple bacteria they evolved a long time ago, more than 2 billion years ago, and they are relatively primitive form of photosynthetic organisms, but they still prosper. As you can see, there are so many different types of photosynthetic organisms, but all of them have the common feature that they consist of 3 important functional parts. The first is called light harvesting, the second is charge separation, and the third is biochemical reaction parts. Probably you learned a lot about these biochemical reaction parts from your biology course some point in your life. But the light harvesting and charge separation parts are relatively unknown to the broader public. it is because they have been kind of understood fairly recently compared to the biochemical reactions. So among all these things, the light-harvesting complexes have very short time scale, about 100 picosecond, and they occur in about 100 nanometer length scales. And they are very efficient. They occur, the loss of energy that are involved in the light-harvesting process is about 0.1 electron volt. So the photosynthesis as a whole itself is not really efficient, maybe about 4 or 5% at the maximum. But the important part is that the light-harvesting part is extremely efficient. It is surely above about 90%. There are various types of light-harvesting complexes that are involved in the light-harvesting process, which means that these complexes collect energies from photons. And although there are various diverse types of light-harvesting complexes, it turns out that there are relatively few types of pigment molecules, such as chlorophylls, bacteriochlorophylls, or billins. So billins are more non-cyclic versions of chlorophylls. Except for the chlorosome that can be found in green sulfur bacteria, in all of these complexes, the pigment molecules are held by protein scaffolds, and they are not really closely packed to each other. They are separated by about 1 nanometer distance from each other. A few years ago, I was asked to write a review article for light-harvesting complexes from an editor of the Reviews of Modern Physics, and was able to complete it about 4 years ago. And it turned out to be, this article actually featured as the cover article of the 90th issue of the Reviews of Modern Physics. So in this article, we provided a review of key experimental and theoretical results, and also provided very comprehensive description of most, not all, if not all, quantum mechanical principles and calculations. And among other things, so we are proud to actually identify important key design principles of these 3 complexes. So today, just 1 hour is too short to talk about all of these things. Today I'm going to focus some important aspects of these light-harvesting 2 complexes that you can find in purple bacteria. So the light-harvesting complexes are known to have excited states in the form of so-called molecular excitons. And the concept of molecular excitons have been known for a long time, and they are nothing but the quantum mechanical linear superposition of individual molecular excitations. So because they are superposition, their energies and sizes are very sensitive to the manner of couplings with the environment. And as a result, it is extremely difficult to identify specific patterns of linear superposition states. But even with that, there is ample evidence that molecular excitons actually exist in light-harvesting complexes. And the fact that they actually play important roles it is well understood. So in more quantum mechanical way, the Hamiltonian that describes the exciton can be expressed this way. So in this expression, this one represents the side excitation state of individual chromophore. And these are electronic couplings. So as a result, these are excitation energy of each chromophore. So typically, the excitation involves the single excitation of pigment molecules such as bacteriochlorophyll or chlorophyll. And the couplings between the pigment molecules mostly involve Coulomb interaction, Coulomb resonance interaction. and some exchange interactions. So it is well known that if the coupling, electronic coupling is much smaller than the energy differences, the excitons are well localized at one pigment molecule. However, if the electronic couplings are much larger than the differences, then the excitons are delocalized all over the chromophores or pigment molecules. Of course, each individual electronic excitation energy is very large, about 1.5 to 3 electron volt. On the other hand, it is known that in most light-absorbing complexes, the electronic couplings are less than about 300 wave number. So just an order of the thermal energy, room temperature thermal energy. But what is important is that they consist of similar pigment molecules. As a result, their energy differences are actually comparable to the electronic couplings. And they are also comparable to the thermal energy, and also comparable to the coupling between electronic excitation and also the surrounding molecular vibrations. And because of that, it is not really easy to classify them as some simple extreme limits. They are typically systems in intermediate coupling regime, and that's why it is actually quite difficult to study and understand them in an accurate way. The light-absorbing complex of purple bacteria was, its structure was determined in 1995 by Kogdal and co-workers. And this is an image of LH2. And the bigger scheme of the photosynthesis of purple bacteria is that LH2 collects photons, and then they create electronic excitation energies in the form of molecular excitons. And then they transport to the reaction center, and then eventually it generates proton gradient across the membrane, and then it provides the energy for purple bacteria. And sometimes these membranes can form vesicles, as you can see here. If you remove all the proteins here, actually they form beautiful circular aggregates of bacterial chlorophylls. And photons are absorbed by these LH2 complexes. And also the LH2 complexes serve as transporter of molecular excitons to the reaction center. Among all the excitations, so-called the QI excitations of bacterial cores play the most important role. And they form so-called 850 and 800 nanometer bands. So these closely packed ones form 850 nanometer band, and this one forms 800 nanometer band. And all of them are superpositions of the QI excitation of the bacterial chlorophyll. Direct evidence for the formation of the molecular excitons were actually reported only around 1999 by single molecule spectroscopy. And this is the ensemble line shape of 800 and 850 band. But the single molecule spectroscopy actually provided the fluorescence excitation spectrum of each complex. And what you see is that each of these actually shows direct evidence of delocalized but discrete levels of excitons. Around 2003, when I was still working as a postdoc, so I was able to kind of come up with a simple theory for line shape, and then was able to reproduce the important qualitative features of the single molecule line shapes. And also, it wasn't that difficult to reproduce the ensemble line shape of the B850 band. But that doesn't mean that I understood everything. In fact, there were so many questions that kind of kept bothering me for a long time. So, or maybe I was really curious about. one of them was that most of the LH2 complexes at that time were known to have 8 or 9-fold symmetries. Why is it so? So no one really had that answer at that time. And also it wasn't clear how some parts actually become 800 nanometer absorber, whereas others become 850 nanometer absorber, even though they consist of the same types of bacterial chlorophylls. So the question is how the excitation energies are tuned. What's the mechanism of that? So we conducted computational modeling some time ago in 2015. We didn't just model the natural ones. We actually became more ambitious and then created synthetic 5 to 12-fold symmetry artificial complexes. So the way we did was that we took out the one symmetry unit of the natural ones, put them together in membrane environment, and then stabilized them, and then saw what happened. So remarkably, we found that all of them kind of, except for the smallest one, we actually tried 3-fold or 4-fold ones, but they became too unstable and they didn't exist. But starting from 5-fold symmetry ones, we were able to actually find out stable forms of synthetic light-absorbing complexes. So that was exciting. So these are the top views of natural and also synthetic LH2-like complexes. So this is the natural one, and all others are kind of something that we created by simulation. But if you look closely, you find that these are mostly circular, but these are more like polygons. And then for these larger ones, there are more, it seems that at local level there is more disorder. So what we find is that when we did the simulation and also did more detailed molecular analysis, we found that the hydrogen bonding actually plays a very important role. So in light-absorbing complexes, for example, in B850, in this case, it consists of 18 bacterial chlorophylls. It is, in fact, 2 concentric rings, one smaller rings and the other one bigger rings. And there are 2 kinds of polypeptides called alpha and beta. So the inner ones are called alpha and the outer ones are called beta. And for natural ones, we find that actually the hydrogen bonding, by the way, the bacterial chlorophylls are mainly held by coordination bonding between histidine unit of the polypeptide and the magnesium center of the bacterial chlorophyll. But it turns out that there are additional bonding, hydrogen bonding. For example, for alpha type of bacterial chlorophyll, there is a hydrogen bonding between tryptophan unit and also the acetyl unit of the bacterial chlorophyll. So that is called, let's call them hydrogen bonding alpha. For the beta type of bacterial chlorophyll, there are different kinds of hydrogen bonding. But based on the simulation results for non-natural systems, we are also able to identify different types of hydrogen bonding. So what was interesting at the time was that, in fact, there are all kinds of different types of hydrogen bonding. First of all, it's possible that none has any hydrogen bonding, or smaller ones. But for the natural ones, like 9-fold one, the alpha-beta hydrogen bonding they are dominant ones. And as you can see that the 9-fold and 10-fold symmetry LH2 complexes are the most stable ones, and then they form consistent natural hydrogen bondings. So what we find is that, let me go back a little bit. What happens is that for the LH2 complexes to be able to form hydrogen bonding, the curvature cannot be too big. So they have to be reasonable size. And that is why you find that for smaller ones, it's very difficult to form hydrogen bonding. But for larger ones, it turns out that there are actually multiple sources of hydrogen bonding, and then the system actually goes through more disorder. But that's not the older story. What we find is that when we actually did the calculation of the excitation energy, what we find is that if the bacterial chlorophyll is actually coupled to, it is actually hydrogen bonded, then its excitation energy actually becomes lower by about 500 wave number. So as a result of that, actually different synthetic complexes actually have different average excitation energy. And if the system actually has consistent hydrogen bonding, there is less disorder. But if there is more chance of non-hydrogen bonding and more hydrogen bonding, there is more disorder in the excitation energy. So what we find is that actually as the system size changes from 5 to 12, we find that the natural ones actually have the lowest excitation energy, and also their disorder becomes the smallest. So this was kind of interesting, although this does not necessarily mean that they are the most stable ones, but what this means is that they have less disorder in the excitation energy. On the other hand, their electronic couplings are not really that sensitive to the size of these things. So our study in 2015 was highly speculative ones, although I felt that we really made great computational discoveries. And since then, actually this year, it turned out that there exists about another new kind of seven-fold LH2 complex. And based on the cryo-EM structure and also computational modeling, they actually found that the seven-fold symmetry ones definitely show evidence of broken hydrogen bonding patterns and also the resulting blue shifts of the B850 band. So this was quite exciting for us because, in a sense, this result validated what we calculated many years ago. Another interesting thing that we also got interested was, we wanted to understand was so-called the LH3 complex. So LH3 complex is kind of the variation of LH2 that is formed by the same organism when the light condition is different. But interestingly, even though LH3 complex is pretty much the same as LH2 in many aspects, their spectral shape is very different from LH2. So what is the source of the spectroscopic difference has been actually the topic of debate for many years. And the common understanding or statement was that maybe this is because of the hydrogen bonding, difference in hydrogen bonding, and also the structural distortion of bacterial chlorophylls. So the reason for this kind of explanation was mostly based on the X-ray crystal structure of LH3, because for the case of LH3, it turns out that the beta bacterial chlorophylls are missing hydrogen bonding, and the alpha bacterial chlorophyll has different kind of hydrogen bonding. And also another important thing is that in LH3, especially the alpha bacterial chlorophylls are distorted a lot. So it was kind of argued that these structural differences are responsible for the spectroscopic difference. But oddly enough, no one really actually calculated the spectroscopic line shape of LH3 successfully. So we got also interested in this system because it is related to what we did earlier. And we also constructed the model for LH3 and conducted molecular dynamic simulations. So what we found is that we also observed the broken hydrogen bonding for LH3 and also alternate hydrogen bonding for alpha bacterial chlorophyll. But the important thing is that the torsional angle of carbonyl group from the molecular dynamic simulation was significantly smaller than that from the crystal structure. This is kind of understandable because the crystal, when they form crystals, they are actually under higher pressure and higher strain. But in natural membrane environment, the torsional angle seems to be a lot smaller. So other than that, all other things are quite similar between LH and LH3. So in actual molecular dynamic simulation, what we find is that the torsional angle actually does not cause much difference in excitation energies. So this turned out to be a little bit mystery. Anyway, we went ahead and then constructed the coarse-grained models. These are some parameters. So the main message is that in terms of these parameters, there's not so much difference between LH2 and LH3. And out of those parameters, we are able to construct coarse-grained quantum mechanical Hamiltonian for LH2 and LH3. So these are some examples. The important thing is that for both LH2 and LH3, it turns out that you can actually model the effect of the older environment and also the molecular vibrations by a collection of linearly coupled set of infinite number of harmonic oscillators. So this is actually quite common model for quantum dynamics, but this is also kind of one of the most criticized models in many of the calculations because sometimes the anharmonic effect can be important. Anyway, within this model, you can actually represent all the effects of the molecular vibrations and environment using some kind of Bath spectral density. So for the calculations that I am showing, we actually extracted that information from experimental data. So here is the rationale for our model. So here is actually a snapshot of LH2 complex in water and membrane that we actually ran for all different kinds of complexes. So I'm not really showing the actual movie of this because it's too large to show in my laptop. And out of that simulation, we actually removed all the protein, lipid, and water molecules and then showing these bacterial chlorophylls. So these are not really simulation of bacterial chlorophylls alone. These are actually movement of all the bacterial chlorophylls in that environment. But interestingly, during this about nanosecond time scale, their dynamics are relatively modest. They do not really go through that significant motion. So here are more local view. So what we see is that although the smaller protein, polypeptides, and water molecules go through significant dynamics, because the bacterial chlorophylls are fairly large, it seems that because they are kind of stuck in pockets of the protein environment, their actual dynamics are relatively minor, at least during this time scale. So this was kind of relieving, and then we kind of used this as the justification for our model. And here are actually three line shapes for three models. The first one is the comparison of theoretical line shape and the experimental ones. They almost agree with each other. So this part is because we neglected the higher vibrational component and also other electronic states. So the main thing is this part. So this actually shows that for LH2, it is possible to model the experimental line shape almost perfectly. But when we actually included all the information from our simulation and then considered only the fact that the beta bacterial chlorophyll has broken hydrogen bonding, but assume that all other are the same as LH2, this is our theoretical line shape, which is very different from the experimental one. So we are kind of disappointed, but this was kind of expected, because if you see, if you have, let's say, so this is a simpler two-level system view. When you have only one of them shifted in energy, if you create symmetric and anti-symmetric linear combination of the two, the lower state wouldn't really change that much compared to the change of one bacterial chlorophyll. So even though one bacterial chlorophyll has significant change in the excitation energy because of the broken hydrogen bonding, this alone is not sufficient to explain the experimental result. So after tinkering with possible reasons and sources of the discrepancy, we came up with some reasonable explanation, which is that if we assume that for some reason all the excitation energies of both alpha and beta for LH3 is shifted up by about 300 wave number, then we are actually able to reproduce the experimental results. So there was no really firm computational data that support our proposal, but there is good justification, because if you look at the actual structure of the symmetry unit of LH2 and LH3, although they are similar, there's some minor and subtle differences between the two. So what we argued was that there is non-specific structural differences in protein units in LH2 and LH3, and they are likely to be the source of about 320 wave number difference in the excitation energies of bacterial chlorophylls. So again, this is kind of the bold but definite statement based on reasoning and also based on our computational results. So we didn't really have clear experimental support for this at that time. But quite recently, there was a paper that actually clarified all the hydrogen bonding patterns based on the cryo-EM image and also computational results. And what they actually show is very consistent with our simulation results. So in a sense, we feel that what we thought and also what we kind of concluded at that time can be really validated more if more experimental data become available. Okay, so far I kind of talked mostly about the structure and also the details of the molecular environment. But more really important thing is the following 3 or 4 questions. How fast excitons can migrate within and between LH2 complexes? And also what makes LH2 complexes efficient and robust energy transfer media, even though there are significant fluctuations and disorder in biological environments. So anything that involves energy transfer, the first inclination is actually to explain with forced resonance energy transfer. So the FRET makes you calculate the transfer rate based on the experimental data, normalize the emission and molar extinction coefficient of the acceptor, and then you calculate the overlap integral. Then you can actually calculate the rate of the excitation transfer. However, this theory cannot be actually applied to multichromaphoric systems such as LH2 complexes. So you need actually a new theory. So in 2004, based on earlier works by Sumi and Scholes and Fleming, so I was able to develop so-called MC FRET, multichromaphoric FRET. And then we were actually able to show that once you apply the theory, it's possible to explain that the exton transfer from 800 to 850 unit becomes about 5 or more factors faster than the prediction based on the first theory. And then afterwards, I was also interested in the transfer rate of exons between different LH2 complexes. But the question is whether it's possible to apply the rate theory such as MC flat, because it is possible that there's not so much time scale separation between intra-LH2 and inter-LH2 dynamics. So to actually account for such possible complications, so when I was visiting Berkeley in 2014, I was able to develop some generalization of the MC flat theory called GME-MED, generalized mass equation approach. So the important thing of this theory is that it actually approaches the Pauli mass equation using MC flat theory once the time scale separation actually happens. So indeed, when we actually apply the theory, we find that at low temperature region, there's significant difference. There's significant non-Markovian effect, but as temperature goes up, such non-Markovian effect actually disappears. So what we find is that around the room temperature, it turns out that the non-Markovian effects, in other words, the lack of time scale separation between intra and inter-LH2 complexes doesn't really matter so much. And as a result, we can safely use the old MC flat theory. So using the theory, but anyway, in all the calculations that I am showing, I am actually mostly showing the result of the GME-MED, although the difference between MC flat is relatively small. So what we find is that, in fact, based on the calculation, we found that the average exon transfer rate between two LH2 complexes is about 0.24 per picosecond. So our prediction is that it takes about 4 picoseconds for exon to transfer from one LH2 to the other. And when you actually convert this to the diffusion constant, it actually shows that it amounts to exons being able to transport about 100 nanometer length scale during its nanosecond lifetime. Another interesting thing is that even though in general the exon transport rate is quite fast, the rate is quite dispersed. So it's because of the intrinsic disorder of individual side excitation energy. So the actual range of the transport time is between 1 to 50 picosecond. And in fact, there has been some experimental report that it is quite broad. So for example, some experimental results based on transient absorption spectroscopy show that it can be at least between 1 to 10 picosecond, depending on realization of disorder. In fact, in actual LH2 complexes, it turns out that, in fact, in actual membrane environment, LH2 complexes do not really form regular crystals. They are quite disordered. The distance between LH2 complexes are not fixed. They are in the range of between 1 and 4 nanometer range, as you can see. So based on that, we kind of assume the possible range of the contact distance between two LH2 complexes being about 1.5 to 4.5 nanometer. And then we applied our theory to calculate the distance dependence of the exon dynamics between two LH2 complexes. These are all logarithmic scale. And if we actually extrapolate the long distance one based on the first type behavior, what we find is that when they are very close with each other, there can be about factor of 10 enhancement due to quantum delocalization of extons. And also, interestingly, there is some kind of resonance enhancement when the two LH complexes are close with each other in their energy, the actual physical distance in natural environment is marked in this region. And these are actually actual energy range of the two LH complexes that are typically observed in natural environment. But in any actual experiment, in explaining actual natural systems or even synthetic systems, it is important to include the realistic effect of disorder. When we actually included the effect of disorder, what we find is that the non-Markovian effects kind of disappear. All the resonance effects also disappear. And in general, there is about factor of 4 reduction in the rate due to disorder. But I think this is still much better than having the single excitation, because the fact is that if you have excitation localized at one pigment molecules, if something happens to that pigment molecules, then the whole process becomes dead. But the nice feature of this delocalized excitation is that, or molecular excitions, is that they are really robust. Even though there are some disorder and defects, it will slow things down, but still they survive and they are being able to be transported to their destinations. Anyway, based on the calculations, we are able to find that LH2 transport times between neighboring light-half and exciton transport time between neighboring LH2 complexes are in the range of 4 to 25 picosecond. Again, I like actually making some kind of quantitative projection, hoping that they can be confirmed experimentally later. So I hope that more experimental data become available, either to test or to validate our results. We also did some more hypothetical study of the calculations. And these are the dependencies of the transport rate as a function of temperature, and also as a function of distance, and also as a function of the amount of disorder. This is a region where there is actually this is a region of naturally occurring disorder. So what we find is that the effect of quantum delocalization and exciton phonon coupling and disorder are, in fact, less important than the inter-LH2 distances. So they are kind of more intrinsic, and they are surely important for determining the rate. But they are more internal properties. But what really serves as the main knob of the exciton transport rate is the inter-LH2 distances. So summarizing all the exciton transport work, so you are actually able to show that the intra-exciton transfer rate can be enhanced by a factor of 5 to 7 because of the delocalization of the exciton. And we also identified an important role of hydrogen bonding. And also we also were able to model the line shapes of LH2 and LH3 complexes. And for the between LH2 complexes, we are able to actually show that there is significant enhancement of inter-LH2 exciton dynamics up to a factor of 10. So overall, the design principle that we are able to identify was that because excitons are delocalized quantum mechanically, they are able to actually help modulate the excitation energy. I mean, they actually make the exciton transport very robust. They become less sensitive to the disorder. But another interesting twist is that there is also an important role by the hydrogen bonding, because they also modulate the excitation energy. going back to the original synthetic LH2-like complexes, so we are interested in how different structural features actually influence the exciton dynamics between LH2 complexes. And here are some different realizations and examples. The main conclusion is that if we actually include all the realistic effects of structure and disorder, we actually find that the natural ones correspond to the maximum inter-LH2 transfer rate on average. So this was quite interesting. So maybe we thought that this can actually justify why natural systems have 9 or 10-fold symmetry complexes in most situations. But when we actually estimated the diffusion constant based on that, the story was not really that simple, because what we actually find is that creating larger LH2 complexes may in fact make exciton dynamics more efficient, but maybe creating larger complexes are thermostatically maybe more costly. So that is why it's not really widely observed in actual natural systems. Or maybe there is additional structural disorder and localization within the ring that may actually result in reduction of actual diffusion constant for larger sizes. Most recently, we also found that, in fact, if we actually align the B850 complexes this way, they may actually serve as efficient light harvesting antennas that can actually transport the excitons quite efficiently across this region. So this kind of suggests that maybe if this kind of synthetic systems can be made, they may serve as an efficient exciton transporter. So let me summarize results for the light harvesting complexes and LH2. So what we find is that quantum delocalization of excitons in the B850 unit of LH2 results in significant enhancement in the exciton transfer rate from B850 to B800 to B850, and also between two B850 units. We also identified important role of the hydrogen bonding, and also we find that proteins serve as good scaffolding environments, and they actually enable small or moderate electron-phonon couplings and disorder, and that is kind of the magic of the protein environments that we find. And another important thing is that in all these light harvesting complexes, including LH2, they are clustered with each other. And because of that, it seems that they actually provide various routes for exciton dynamics. So if one path actually fails, it makes the other path available. And I called that quantum buffering, but unfortunately, the term called quantum buffering has different meaning in quantum information science. So it's not easy to actually kind of promote this idea unless I use different name. So I think I have about 10 minutes, although I finished only about, I think, 60%. So let me kind of quickly go through the 5 criteria of excitons for solar energy conversion that I was able to identify based on our computational study. And what we find is that, amazingly, natural systems actually have all these 4 components. So these features are kind of already inherent in the natural systems. And for biological systems, actually creating this fine-tuning and also the molecular complexes don't appear to be that difficult. But if you actually think of creating this synthetically, it seems that they are actually very costly. And I also find that that is actually the case in actual synthetic systems. Quite recently, I was involved in some collaboration with this kind of synthetic light harvesting complexes. And the great thing about this system is that a protective layer around the chromophore aggregate can help robust exciton dynamics. But the problem is that satisfactory understanding of the disorder and fluctuations and their effect on delocalized exciton still remain very difficult issue to model and also understand. There has been also great interest in utilizing triplets for efficient solar energy conversion. And this particular example seems to be promising because it actually shows that because of the delicate balance of moderate couplings, there is great enhancement in triplet generation. But even for these synthetic systems, we find that reliable spectroscopic modeling of aggregates and clear mechanistic understanding of triplet generation remain very difficult. Let me go back to the first image that I showed before. In fact, this is the simulation of LH2 complex in membrane. It is the outcome of about 48 nanosecond simulation that we used the computer called Anton that was used in early days for long-time protein simulation. And if you actually accumulate all of the results for about 1,000 nanosecond time scale, you see that there's great backbone fluctuations. So the main challenge for even for these kinds of systems is that fortunately our results were based mostly on short time, maybe nanosecond time scale dynamics. But maybe it's important to be able to gain reliable modeling and understanding of all the effects of fluctuations at different lengths and time scales. And going forward, maybe it'll be great if someday we are able to do all atomic simulation of not just one LH complex, but aggregates of these LH complexes. I think it's possible with current computational technology, but just it is so expensive. And as yet, there is no really clear justification for why that has been done. But there is always surprise in calculation results. I have only about 5 minutes. Let me go through kind of the second part of my talk very quickly in about 5 minutes. So the main thing is that I think this is the main thing that I want to show. Over the years, I was able to develop various generalizations of the force theory, as you can see here. And some of them were applied to LH2 complexes and different organic molecules. And for example, for each theory, I was able to derive very simple rate expressions. Although they are more complicated than the original force theory, they are still applicable to many systems, as you can see. More recently, I was involved with more advanced level of the quantum mass equation theories for more involved quantum dynamics. One application of this was the exciton dynamics between these two units that experimentally they observed coherent dynamics. And we are actually able to reproduce the experimental data given that we identify the right parameters that are also consistent with our independent computation results. And also, the effect of the coherence can actually cause deviation from the 1/r⁶ dependence, even when the electronic coupling is purely transient dipole interactions. So a recent book that I wrote actually contains all those theories. And most recently, we are interested in understanding the exciton dynamics between these two units. And it turned out that they all deviate from the prediction of the first theory. For larger ones, they can be actually explained if you use more accurate computational results. But for smaller ones, even if you include all those effects, still there was some difference, about factor of 2 difference between theoretical and experimental results. So I was able to kind of explain the major source of the difference. Based on my theoretical analysis, our theoretical analysis, so we find that the bridge unit has provided additional source of the vibration, and the effect of the bridge unit doesn't cause so much difference in the line shape. However, they actually result in significant difference in the rate. And the difference between those two actually is sufficient to explain the deviation of the rate from the first theory. More recently, the energy gap law is also important theory that has been used a lot for now light emitting diode, and also for new development of the dye molecules for bioimaging. But I was also able to find more generalized version of the energy gap law, and the application of the theory actually shows that the black line is the result of my theory, and this is the original Jordan and Engels theory. Even though in this case it appears to reproduce the qualitative result, there is significant difference between the actual exact result and the Jordan Engelmann's theory. And the new theory is capable of actually almost agreeing with the exact calculation here. So I'm sorry that I kind of rushed it through important details at the last minute, but I'm happy that I have really completed all those things that I wanted to talk about. So finally, I want to give you more bigger overview of the types of research I've been doing. So in a sense, I was always interested in some sort of quantum dynamics calculations. There are various ways of doing that, but mostly I relied on combining computation, spectroscopy, and simulation, and then develop coarse-grained models. This is not really that all is simple, because you also need to develop right theory and also right methodologies. But the nice thing of having all these in one group is that we actually understand the approximation assumptions involved in different theories, and it is possible to apply the right theory for right system. So I had a good time of doing these kinds of research up to now, but in longer term, I am interested in doing more all-atomistic computational methods that can provide quantitative description of quantum coherence, tunneling, and non-linearity and anharmonicity. And I see great opportunity of collaborating with Professor Youngmin Lee and also other members of the department. And going forward, I plan to push this more and then work more on chemical sensing, quantum sensing, and information at molecular level. Because right now there is great interest in quantum sensing and quantum information processing, but most of the research topics are either very simple atoms or solid state materials. I think there's great chance of developing new types of quantum sensing and information processing devices using complex molecules. And in doing so, I think also it's important to be able to combine also machine learning approaches. But again, so far, all the machine learning approaches have been kind of applications of already well-established methods that were developed in computer sciences in general, or maybe other parts, engineering. But I think that it is also important, it is right time to develop new types of machine learning approaches that can actually provide smooth interface between already existing theories and new computational and experimental data. So these are kinds of things that I am currently interested in, and hope to be able to make some progress going forward. And finally, I'd like to thank all of you for paying attention to my talk, and I'm happy to answer any questions. Thank you.